Step into this cramped steel coffin. Feel 45 tons of metal pressing down through narrow tracks. Your hands clutch sluggish controls that respond as if frozen in winter. The engine growls behind you, a temperamental beast that could stall at any second. Welcome to the Panther, Germany's so-called superior tank. The same machine that broke more often than it battled. The same vehicle that spent more time in maintenance depots than on front lines. What Allied crews uncovered inside these captured German wonders shattered long-held assumptions about tank warfare and forever altered the debate over one of history's most famous pieces of engineering. December 1944, the snow-blanketed forests of the Ardennes. American tankers crouched in their Shermans, watching German armor emerge through the fog. Panthers, sleek predators of the battlefield. 45 tons of sloped armor and a deadly 75mm high-velocity cannon. Every U.S. tanker had heard the rumors. One Panther could face 5 Shermans. Its 80mm glacis plate angled at 55 degrees gave protection equivalent to nearly 140mm. The turret front was 100mm thick. Its WWII 42 L-70 gun could pierce a Sherman from over 2 kilometers away. American crews grimly called their own tanks Ronsons after the lighter, lights every time. Climbing into their 33-ton Shermans that frozen morning, they knew the odds. The Panther outgunned them. Its frontal armor could shrug off their 75mm shells. In a head-on duel at range, they were outmatched, and both sides knew it. German tankers were told their Panthers were invincible, that Allied tanks were inferior in every way. Propaganda reels showed German steel crushing Allied machines, Panther triumphing over mass production. The Panther had been created to counter the Soviet T-34 after the shock of encountering T-34s during Operation Barbarossa in 1941, especially at the Battle of Mtsensk that October. The German High Command convened a Special Tank Evaluation Committee. The Panther Commission formed in November 1941. Mann's design was approved by May 1942. The first prototype rolled out that September, and mass production began in January 1943. On paper, it was flawless, the ultimate medium tank. Every specification favored the German design. Yet as Allied forces advanced deeper into Germany, a strange pattern appeared. Recovery teams kept finding Panthers simply abandoned, not destroyed by fire or mines, but left behind by their crews. Engines cold, fuel in the tanks, transmissions seized, final drives shattered. Some Allied units even tried using captured Panthers. The British Coldstream Guards famously operated one they nicknamed Cuckoo during fighting around Geilenkirchen, and later in Operation Blackcock. January 1945. Canadian troops captured an intact Panther in Italy in October 1944, dubbed it the Deserter, and used it in several assaults before sending it for analysis. In Warsaw, resistance fighters seized 2 Panthers during the August 1944 uprising. They used them to wipe out German machine gun nests and free prisoners from the Gesiowka concentration camp. 348 people saved. Within days, both tanks were immobilized by lack of fuel and batteries and had to be burned to avoid recapture. The story was always the same. Captured Panthers fought fiercely, for a while. Then, they broke down. After the war, the British assembled 9 Panthers from spare German parts and attempted standard trials in 1947. They couldn't finish them. The Panthers failed repeatedly. The official report concluded, very little of practical value could be learned due to the general mechanical unreliability of the Panther. The French Army, which also operated captured Panthers post-war, produced the most detailed technical evaluation. Their 1947 report, Le Panther, stated bluntly, "The Panther's true weakness is its final drive. Of too fragile a design, with an average fatigue life of only 150 kilometers. Think about that. Less than 100 miles before the crucial components transferring power to the tracks needed total replacement. German wartime records confirmed it. General Guderian wrote in June 1944, "The life expectancy of the Panther's engine, at 400 to 1500 kilometers, far exceeds that of its final drives. A solution to this problem is urgently required." Reports from the Eastern Front between March and April 1944 noted that 13 final drives had been replaced in just 30 Panthers. A January 1945 Panther Commission document listed 370 defective final drives awaiting replacement. Half of all Panthers abandoned in Normandy showed final drive failure as the main cause. The reason was simple. Man's initial plan used planetary epicyclic gearing, but shortages of precision gear-cutting equipment forced a change to a double spur gear setup, a design that suffered from high internal stress loads. The drivetrain was originally meant for a 35-ton tank, but Hitler demanded more armor and a bigger gun. The finished Panther weighed 45 tons. The drive housings, never reinforced, flexed under stress, destroying the gears. Sherman final drives, in contrast, could run for thousands of kilometers without major issues. French experience operating captured. Panthers from 1946 to 1950 confirmed the 150 kilowatt breakdown rate again, and, again, even the Maybach HL230 engine, powerful, on paper at 690 horsepower, was notoriously unreliable. During Operation Citadel at Kursk in July 1943, Panzerabteilung 51 recorded 20 fuel pump failures by July 8 alone. Leaks caused several Panthers to burn completely. Some caught fire just rolling off transport trains. Typical engine issues included cracked cylinder heads, snapped connecting rods, failed oil pump drives, leaks causing engine fires, cooling fan bearing failures, and chronic overheating. By late 1943, the Germans were forced to reduce engine RPM from 3,000 to 2,500 to extend service life, cutting top speed from 34 mph to 28 and power from 700 HP to 580. Even then, the average Panther engine lasted barely 1,000 kilometers. French post-war data confirmed it, with only a few reaching 1,400–800 kilometers before total failure. The Panther's turret system added more headaches. Early AOSF-D versions used a single-speed hydraulic traverse that took nearly a minute to rotate a full circle. Later, AOSF A and G variants adopted two-speed gearing. At 2,500 RPM in high gear, a full 360-degree rotation still required 17 to 18 seconds. At low RP in low gear, traverse time extended to 60 to 93 seconds. The system's performance varied constantly with engine speed. If the engine died, the turret could not traverse at all. The Sherman, by contrast, used an independent auxiliary electric motor. The Sherman's turret always rotated in 15 seconds, regardless of engine speed. The commander could traverse the turret even with the main engine off using the backup generator. This consistency provided enormous tactical advantages. The Panther's, theoretically, faster traverse at optimal engine speed was meaningless when mechanical failures stopped the engine or when tactical situations required turret movement while the engine idled. The 7-speed manual transmission was stiff and difficult to shift. Every gear change was a battle. Sherman transmissions were smooth and nearly automatic in operation. The Panther's narrow track width, despite good ground pressure on paper, meant less actual contact with soft ground. In mud or snow, Panthers frequently became stuck. Their excellent cross-country performance applied only to firm, dry terrain. The Sherman's wider tracks provided superior real-world traction in varied conditions. Crew ergonomics in the Panther were poor. The interior was dark and cramped. The gunner's position was more confined than in a Sherman. The loader had to reach across the large gun breech in awkward positions to access ammunition scattered around the fighting compartment. The Sherman's ammunition storage featured ready racks within easy reach of the loader. Everything was organized logically. American automotive engineers had designed the Sherman using the same human factors principles they applied to automobiles. Make it easy for the operator. By March of 1945, the complaints from American tankers about facing Panthers and Tigers had reached General Eisenhower repeatedly. He wrote to the commanding generals of the 2nd and 3rd Armored Divisions, asking for detailed assessments. General White, commander of 2nd Armored Division, prefaced his reply by asking Eisenhower to make allowances for the traditional enthusiasm displayed by the American soldier when given the opportunity to express himself regarding any possible shortcomings in his equipment. General Collier, commander of Combat Command A of 2nd Armored Division, provided a detailed assessment. The consensus of opinion of all personnel in the 66th Armored Regiment is that the German tank and anti-tank weapons are far superior to the American in the following categories: superior flotation, greater mobility, better gun sights, and higher velocity guns, smokeless powder that made German tanks harder to spot, better sloped armor and better silhouette. Collier then contested Eisenhower's rationalization that American equipment limitations were justified by shipping distances. The fact that our equipment must be shipped over long distances does not, in the opinion of our tankers, justify our inferiority. This was March 1945. The war in Europe would end in May. Eisenhower replied immediately, "I feel that your conclusions should go at once to the War Department, and I am sending them on to General Marshall without delay." Too late for any changes to affect the outcome. But these documented assessments reveal that American tankers clearly recognized the Panther's advantages in direct combat. They wanted better tanks. They were not blind to the Sherman's limitations. Yet they won anyway. Not despite the Sherman, but because of what the Sherman represented: a complete weapon system optimized for total war. Between June and December 1944, the 12th Army Group lost more than 2,000 medium tanks, mostly Shermans. These losses shocked the American public when soldiers' letters home and press reports revealed the scale of tank casualties. In January 1945, New York Times correspondent Hanson Baldwin wrote critical editorials urging congressional inquiry into American tank adequacy. The Army leadership responded with articles defending the Sherman. Major General Levin H. Campbell, Jr., Chief of Ordnance, released Eisenhower's letter to diffuse further criticism. After the war, General Marshall tried to explain American tank performance, acknowledging that from summer 1943 to spring 1945, German Tigers and Panthers outmatched Shermans in direct combat. But Marshall's explanation emphasized that American doctrine never intended for medium tanks to fight heavy tanks alone. Tank destroyers, artillery and air support were meant to neutralize heavy armor, while medium tanks performed their primary role of exploiting breakthroughs and supporting infantry. The Sherman's combat record, examined beyond individual engagements, demonstrates overall effectiveness. American and British forces landed in Normandy in June 1944. By May 1945, 11 months later, Allied armies had advanced from the French coast to Berlin, conquered Germany, and ended the war in Europe. German forces equipped with technically superior armor could not stop this advance, not because Panthers and Tigers were ineffective in battle. They were deadly when they fought, but because they could not fight consistently enough to matter strategically. A tank that breaks down before reaching battle provides zero combat power. A tank immobilized by lack of fuel contributes nothing. A tank awaiting spare parts that never arrive becomes a stationary pillbox. Strategic effect requires sustained operations over time and distance. The Sherman provided sustained operations. The Panther did not. The Sherman succeeded because it prioritized the right factors: not gun penetration at maximum range, not armor thickness in frontal engagements, but reliability, maintainability, crew survivability, production capacity, logistical sustainability, and tactical flexibility. Consider the Sherman's five-man crew layout: commander, gunner, loader, driver, assistant driver, who also operated the bow machine gun. The crew positions allowed efficient operation and good crew coordination. Multiple escape routes included a large belly hatch, side hatches, and turret hatches. When a Sherman was hit, crews had excellent chances of escaping. The British, after studying captured Tiger 131, used its technical details to help design the Sherman Firefly with the 17-pounder gun. Sherman variants addressed different tactical needs. The M4A3E2 Jumbo featured 120 mm glacis armor and 152 mm turret front armor. Fisher Tankersinnel produced 254 Jumbos from May to July 1944. These were deployed as breakthrough tanks to lead assaults. The wet ammunition storage system introduced in Sherman production placed ammunition in water glycol-jacketed bins. This reduced fire probability when penetrated from 60 to 80% down to 10 to 15%. This single improvement saved thousands of crew lives. The 76mm M1 gun, introduced in January 1944 and first seeing combat in July 1944 during Operation Cobra, provided improved armor penetration. However, the 76mm gun had significantly worse high-explosive performance than the 75mm. The 75mm M48 round produced 50 effective fragments in a 20 FT radius. According to U.S. Army Technical Manual 9-1907, the 76mm M1 produced only 560 fragments. The reduction in H-effect effectiveness was a real tactical limitation that many units preferred to void. American tankers understood that tanks fought infantry far more often than they fought other tanks. High explosive effectiveness mattered more in most combat situations than armor-penetrating capability. The Panther's 22 PA-42L72 gun, optimized for anti-armor performance with its high velocity and long barrel, fired a weaker H-shell compared to lower-velocity weapons. High-velocity, long-barrel guns sacrifice explosive effectiveness for armor penetration. You cannot optimize for both simultaneously. Israeli forces recognized the Sherman's fundamental soundness. They modified, captured, and purchased Shermans extensively. The M50 Sherman, with a French 75mm gun and Continental R975 engine, served from the 1956 Suez Crisis through the 1967 Six-Day War and the 1973 Yom Kippur War. The M50 Continental Mark I retired in 1972. The M50 Cummins M2 served into the late 1970s. The M51 Sherman mounted a French 105mm gun. It served from 1965 into the early 1980s. Israeli M51s successfully engaged modern Soviet T-54, T-55, and T-62 tanks using 105mm heat rounds. Israel sold 75 M51s to Lebanese militias in 1976 and over 100 to Chile, which used them until 1999 and kept some in reserves until 2006. This operational longevity from World War II through the 1970s and 80s demonstrates the Sherman's fundamental design, soundness, and adaptability. Now, consider the Panther's systemic failures. Production totaled approximately 6,000 vehicles between January 1943 and March 1945, not 9,000 as commonly stated. Multiple authoritative sources confirm 6,000 as the accurate total, with some sources citing specifically 5,164 built. Peak monthly production reached 382 in July 1944, but averaged far lower. Frontline combat strength peaked on September 1, 1944, at 234 tanks. But that same month, a record 692 tanks were reported lost. The last operational report, dated March 15, 1945, lists only 361 operational out of 740 Panther tanks total. Only 49% operational at war's end. Allied bombing targeted Panther production facilities. Daimler-Benz was struck on August 6 and August 23, 1944. MAN was bombed on September 3, October 3, October 19, 1944. Then again on January 3 and February 20 to 21, 1945. These raids forced spare parts production to plummet from 25 to 30% off tank production in 1943 to only 8% in late 1944. Panthers in the field had to be cannibalized for parts to keep others running. The lack of spare parts compounded mechanical reliability problems. German crew training quality declined severely as the war progressed. Historian Stephen Saga observed that the Panthers' disappointing performance in the Ardennes against American Shermans, despite superior technical specifications, resulted from poor crew quality by this point in the war. Most Panther crews were inexperienced with minimal training. Lack of training exacerbated the Panthers' technical weaknesses. The combination of poor powertrain durability, lack of fuel, lack of spare parts, and inexperienced crews resulted in many Panthers breaking down and being unable to be recovered or repaired. The French 1947 report noted that poor training of drivers was a principal cause of Panther mechanical defects. The battalion has received drivers who are operating a Panther for the first time. Tanks are being written off for quite minor technical problems. Fuel shortages crippled German armored operations. Panthers consumed massive amounts of fuel. German logistics could not sustain fuel supplies to forward units. Soviet tanker Dmitry Loza, hero of the Soviet Union, commanded American-supplied Shermans on the Eastern Front. He documented his experiences in the book Commanding the Red Army's Sherman Tanks. In an interview, Loza stated directly, "The service life of the Sherman track was in excess of 5,000 kiloliters." He praised Sherman reliability extensively, noting the auxiliary gasoline engine for charging batteries that eliminated the need to run the full 500 horsepower main engine. He commended superior American armor quality with no interior spooing, comfortable crew stations, and general mechanical reliability. He noted the Sherman drove like a car on hard surfaces, and RT-34 made so much noise that only the devil knows how many kilometers away it could be heard. The Sherman's cost efficiency enabled mass production. Initial M3 and early M4 Chrysler contract prices in 1940 to 1942 were $33,000 to $33,500. Later variants ranged from $44,556 to $64,455 depending on model. Official U.S. Army catalog prices in August 1945 listed most Sherman models at $44,000 to $55,000. Total Sherman production reached 49,322 units from 1942 to 1945. Not 50,000 as commonly rounded, but 49,324 documented units. American industry produced these vehicles across multiple manufacturers using standardized parts and efficient assembly methods. The Panther's base cost was 117,100 Reichsmarks, excluding armament and radio. With the Quip K-42 gun and equipment, combat-ready cost reached approximately 143,912 Reichsmarks. German industry struggled to produce even 6,000 Panthers, despite enormous effort. American doctrine emphasized combined arms integration. Shermans operated with infantry, artillery, tank destroyers, and air support. American commanders understood that tank versus tank battles were relatively rare. Most tank combat involved supporting infantry, destroying fortifications, and engaging soft targets. The Sherman's reliable mobility and excellent H performance made it ideal for these missions. American tank destroyer battalions equipped with M10, M18, and M36 tank destroyers provided dedicated anti-armor capability. The M36, with its 90mm gun, could penetrate Panther armor more effectively than Sherman's. During the Battle of the Bulge, M36 equipped battalions, including the 610th, 73rd and 740th Tank Destroyer Battalions proved highly effective against German armor. 4 M18s, along with M4 Shermans and infantry from 10th Armored Division, occupied Noville north of Bastonia and stopped a German armored attack with flank fires, destroying 30 heavy tanks, including Panthers and Tigers. The Battle of the Bulge in December 1944 and January 1945 tested American armor doctrine under the worst conditions. Hitler's Ardennes offensive launched on December 16, 1944, with approximately 2,500 tanks and assault guns in 24 divisions, including 10 Panzer divisions. The main thrust fell on the 99th and 2nd Infantry Divisions. German forces achieved surprise and initial success. American units, including the 740th Tank Battalion, scrambled to respond. Men pieced together damaged tanks from depot stocks, sometimes finding dead crews still inside vehicles that smelled of death. They managed to assemble 3 M4 Sherman tanks and 1 M36 tank destroyer. On December 19th, this small force engaged elements of SS Lieutenant Colonel Joachim Peiper's battle group equipped with Panthers and King Tigers at Stoumont. The improvised American tank force knocked out 3 Panthers, helping halt Peiper's spearhead. Throughout the Bulge fighting, American tank destroyers proved their value. Towed anti-tank guns were ineffective in the cold, wet weather and rough terrain. Throughout First Army, 3/4 of towed tank destroyers lost were total losses. The 8001st Tank Destroyer Battalion, equipped with towed guns, lost 17 guns in just 2 days. The 644th Tank Destroyer Battalion, equipped with M10 self-propelled guns fighting alongside them, found ideal opportunities for close-range ambushes and claimed 17 German tanks in the same period. The contrast convinced Eisenhower to approve conversion of all remaining towed units to self-propelled guns in January 1945. The M36, just entering service when the offensive began, proved highly effective throughout the Ardennes campaign. Its 90mm gun, the same armament carried by the M26 Persian heavy tank, beginning Toriach frontline units, could engage Panthers and Tigers on more equal terms. American logistics enabled sustained operations. Sherman engines used readily available gasoline. Spare parts flowed continuously from factories to frontline units. Maintenance could be performed by moderately trained crews. Battle-damaged Shermans were recovered, repaired, and returned to service rapidly. The U.S. 3rd Armored Division entered combat in Normandy with 2 132 M4 Sherman tanks. During the entire European campaign, the division had approximately 648 Shermans completely destroyed in combat and another 700 knocked out, repaired, and returned to operation. This 580% loss rate sounds catastrophic, but it demonstrates the Sherman's greatest strength: the ability to be produced in such numbers that losses could be continuously replaced, the ability to be repaired and returned to service, the logistics system that kept replacement tanks flowing forward. German armored divisions, by contrast, saw their strength decline throughout the campaign as losses could not be replaced. The Battle of Aricourt in September 1944 demonstrated American tactical superiority, despite technical inferiority. The 4th Armored Division's 37th Tank Battalion, commanded by Lieutenant Colonel Creighton Abrams, operating from his Sherman Thunderbolt, engaged German forces, including newly arrived Panther-equipped units. Abrams went through 7 different tanks during the war, but always commanded Shermans. At Aricourt, his battalion lost 14 Shermans while destroying 55 Panthers and Tigers. General Patton called Abrams the world champion tank commander. The engagement demonstrated that properly employed Sherman tactics utilizing terrain, combined arms, and aggressive maneuver could defeat technically superior German armor. The Sherman won World War II. Note alone, but American armored divisions equipped with Shermans spearheaded the breakout from Normandy, the drive across France, the crossing of the Rhine, the conquest of Germany. They accomplished this against German forces equipped with Panthers, Tigers, King Tigers, and Jagd Panthers. Technically superior German armor could not stop American armored operations because wars are not won by technical specifications alone. Logistics wins wars. Reliability wins wars. Production capacity wins wars. Combined arms integration wins wars. Crew confidence wins wars. Adaptable doctrine wins wars. The Sherman embodied all these factors. The Panther embodied impressive specifications but failed at systemic integration. When Soviet forces captured Panthers and attempted to use them against Germans, the vehicles performed briefly, then broke down. A February 1945 Lower Silesian offensive saw one captured. Panther, with an experienced crew from 4th Tank Corps, under command of Hirov, the Soviet Union Lieutenant Nikolai Ivanovich Agia, used in a reconnaissance mission. At dusk, the tank passed through forest, attacked from the flank, and destroyed 3 enemy Panthers. During retreat to Soviet positions, it was hit by German artillery and damaged. After the battle, the tank was written off due to lack of spare parts and maintenance problems. Even when operated by skilled Soviet crews, captured Panthers proved unsustainable. The systematic analysis of tank effectiveness must account for the entire weapon system. Design, production, logistics, maintenance, doctrine, crew training, tactical employment, and sustainability. The Panther excelled at a narrow set of specifications: gun penetration at long range, frontal armor protection in direct engagement, speed on good terrain. But it failed catastrophically at reliability, maintainability, production efficiency, logistics sustainability, crew ergonomics, and operational availability. The Sherman provided adequate performance in gun and armor specifications while excelling at reliability, maintainability, production efficiency, logistics sustainability, crew ergonomics, escape provisions, and operational availability. In total war, adequate technical specifications combined with superior systemic factors defeat superior technical specifications combined with inferior systemic factors. Every time the lesson transcends World War II, the lesson transcends tank design. Any weapon system, any tool, any technology must serve its users under real-world conditions, must function reliably when needed most, must be maintainable with available resources and infrastructure, must account for human factors in operation and maintenance, must integrate effectively with other systems, must align with operational doctrine, must be sustainable through the logistics chain, must be producible in quantities that meet demand. Technical excellence that ignores these factors produces expensive failures that look impressive on paper but collapse under operational stress. Practical adequacy that embraces these factors produces war-winning tools that perform reliably under the worst conditions. The Panther's development, rushed into production after encountering T-34s, never achieved theme maturity needed for reliable field operations. Its combat debut at Kursk in July 1943 was disastrous with widespread mechanical failures. Improvements reduced but never eliminated the fundamental design flaws. The final drive problem, rooted in weight growth beyond original design parameters, was never solved. Engine reliability improved somewhat, but remained poor compared to Allied tanks. The complexity of the design exceeded German industrial capacity to manufacture with adequate quality control, especially as Allied bombing damaged factories and disrupted supply chains. The Panther represented German engineering's tendency toward over-optimization for specific parameters at the expense of overall system effectiveness. The Sherman represented American industrial pragmatism, design for manufacturer, design for maintenance, design for logistics, design for the crew. The Sherman was never intended to be the best tank by any single metric. It was intended to be good enough at everything while being excellent at the factors that mattered most for sustained operations: reliability, maintainability, producability. The automotive industry's mass production expertise applied to plate tank manufacturing created a weapon system that could be built by the thousands and sustained across global supply lines. Ford, Chrysler, General Motors, American Locomotive Company, Baldwin Locomotive Works, Lemur Locomotive Works, Pacific Car and Foundry Company, and others produced Shermans using standardized components and efficient assembly methods. The last Panther rolled off production lines in March or April 1945. By then, many were being abandoned before even reaching combat units due to lack of fuel and trained crews. The last Shermans rolled into Berlin in May 1945 as the war in Europe ended. Israeli-modified Shermans fought in the Yom Kippur War in October 1973, nearly 30 years after the war ended. This operational longevity gap of 3 decades between the Panther's extinction and the Sherman's continued evolution illustrates which design philosophy proved more sustainable. The Panther was a developmental dead end. No post-war tank designs borrowed significantly from it. The Sherman influenced post-war tank development globally because its fundamental approach, prioritizing reliability and maintainability alongside combat capability, represented the correct balance for practical military operations. American tankers in 1945 understood these truths through direct experience. They faced Panthers in combat. They recovered abandoned Panthers from the battlefield. Some units evaluated captured Panthers. They recognized the Panther's advantages in direct engagements, but they also recognized the Panther's fatal weaknesses in sustained operations. They understood that a tank unable to reach the battlefield due to mechanical failure provides zero combat power. They understood that a tank burning through fuel faster than logistics can supply becomes immobile. They understood that a tank requiring specialized parts unavailable in the field becomes scrap metal. They understood that a tank with inadequate crew escape provisions becomes a death trap when hit. The Sherman's nickname as Ronson later reflected the real fire danger from ammunition stowage in early models. This was a serious problem that cost lives. American engineers responded with wet ammunition stowage, dramatically reducing fire risk. German engineers made no equivalent improvements to Panther survivability. The Sherman's relatively thin armor was a real vulnerability in direct tank combat. American doctrine responded by emphasizing combined arms, avoiding frontal engagements when possible, and using tank destroyers for anti-armor missions. German doctrine emphasized increasingly heavy armor on new tank designs, resulting in vehicles too heavy for their drivetrains and too expensive to produce in adequate numbers. Different approaches, different results. The American approach won. The statistical evidence is overwhelming. 49,324 Sherman tanks produced, 6,000 Panthers produced. Sherman operational availability rates remained high throughout the war. Panther operational availability declined to 49% by March 1945, American. Armored divisions maintained combat effectiveness from Normandy to Berlin despite heavy losses because the logistics system continuously replaced losses. German armored divisions declined in strength throughout the campaign as losses exceeded replacement capacity. American combined arms doctrine integrated tanks with infantry, artillery, air support, and specialized vehicles effectively. German doctrine increasingly relied on tanks alone to compensate for declining infantry and artillery capability. Understanding the Sherman's success requires examining American industrial mobilization. When war began, American automotive manufacturers converted production lines from civilian vehicles to military equipment. Ford's River Rouge plant, Chrysler's tank arsenal, General Motors facilities, all transformed to produce tanks using assembly line methods perfected for automobile production. Workers who had built cars applied the same efficiency principles to building tanks. Standardization of parts across manufacturers meant a transmission from one factory fit a hull from another factory. A gun mount from Fisher Tank Arsenal matched a turret from American Locomotive Company. This interchangeability, commonplace in automobile manufacturing, but novel in military production, enabled unprecedented production rates and simplified field maintenance. The Sherman design prioritized ease of manufacture, curved armor plates, while more resistant to penetration, require expensive dies and specialized presses. The Sherman used largely flat armor, plates that could be cut and welded efficiently. The cast turret could be produced in large foundries using techniques adapted from civilian heavy industry. The suspension system used vertical volute spring units, simple and reliable, that could be manufactured by companies with no previous military experience. Every design choice reflected the priority of mass production without requiring specialized tools or techniques. Training new tank crews in the Sherman took approximately 13 weeks at armored training centers. The layout was intuitive for men familiar with automotive equipment. The controls responded predictably. The maintenance procedures documented in clear technical manuals could be learned by mechanics with basic automotive background. German Panther training required longer periods and more specialized instruction due to the vehicle's complexity. As German losses mounted and training time shortened, crew quality declined. American training pipeline, by contrast, maintained consistent standards throughout the war, producing adequately trained crews at the rate operations demanded. The Sherman's maintenance advantages became apparent in sustained operations. An average Sherman engine change required 8 to 10 hours with a trained crew and proper equipment. The power pack, engine, and transmission together could be removed and replaced as a unit. Armored divisions carried spare power packs on trucks, following advancing tank columns. A disabled Sherman could be back in action within hours. Panther engine removal required significantly more time and specialized equipment. The engine and transmission were separate units, each requiring individual removal procedures. Field maintenance of Panthers often proved impossible, requiring tanks to be towed long distances to depot-level facilities. Many Panthers were abandoned after relatively minor failures because repair in the field was impractical. Sherman track replacement could be accomplished by the crew in the field in 3 to 4 hours per side. The track blocks were relatively lightweight and could be handled by 2 men. Panther tracks were heavier and more difficult to work with. The interrolled road wheel system, while providing excellent ride quality, meant that if an inner road wheel was damaged, multiple outer wheels had to be removed first to access it. In winter conditions, mud and snow froze between the interrolled wheels, immobilizing Panthers until extensive desing efforts were completed. Shermans, with their simpler suspension and independently mounted road wheels, did not suffer this vulnerability. The logistics tail for Sherman operations was extensive but sustainable. Each armored division required thousands of tons of fuel, ammunition, spare parts, and supplies monthly. American logistics units delivered these supplies reliably across growing distances as armies advanced through Europe. The Red Ball Express, a truck convoy system, delivered 7,000 tons of supplies daily at its peak. Liberty ships brought material from American factories across the Atlantic. The logistics system worked because it was planned, resourced, and executed as an integrated whole. German logistics, by contrast, collapsed as Allied bombing destroyed rail networks, fuel production facilities, and transportation infrastructure. Even when Panthers were mechanically sound, lack of fuel immobilized them. Sherman fuel consumption, while substantial, remained within logistical sustainability. Combat operations consumed fuel at high rates, but American logistics could deliver adequate supplies continuously. Panthers consumed fuel at similar or higher rates, but German logistics could not maintain supply. The difference was not vehicle consumption, but logistics system capacity. American logistics was built to support mechanized warfare on a global scale across ocean supply lines. German logistics was designed for relatively short campaigns within Europe and collapsed under sustained Operations and Allied interdiction. The Sherman succeeded because it was designed, produced, and employed as part of a complete military system. The Panther failed because it was designed as a technically superior weapon without adequate consideration for the system required to sustain it in combat. Warfare fought by systems, not by weapons. The side with the better system wins, even when the enemy has better weapons. The United States in World War II built and sustained a military system capable of projecting power globally, supplying forces across oceans, maintaining equipment in harsh conditions, training replacement personnel continuously, and adapting doctrine to changing circumstances. Germany built increasingly sophisticated weapons that its industrial base could not produce in adequate numbers. Its logistics network could not sustain in the field. Its training pipeline could not provide adequate crews for, and its tactical doctrine could not employ effectively given declining resources. Post-war analysis by military professionals confirmed these conclusions. The French Army operating captured Panthers from 1946 to 1950 in the 5001st and 5003rd Armored Regiments documented every mechanical failure and operational limitation. Their 1947 technical evaluation, Le Panther, became the definitive study of the tank's actual performance under real operational conditions. The report confirmed the 150-kilometer lifespan of the final drive, the 1,000-kilometer engine life, the difficult maintenance demands, excessive fuel consumption, poor crew ergonomics, and tactical shortcomings. French engineers and crews, initially impressed by the Panther's impressive specifications, ultimately concluded that the Sherman was the superior fighting vehicle when all factors were considered. They acknowledged that certain features of the Panther, especially its main gun and optics, were admirable, but the overall machine proved unsuited for extended combat operations. The British post-war testing reached nearly identical conclusions. After capturing numerous Panthers during the Northwest Europe campaign, British authorities took control of a German Panther assembly plant in Hanover, following the surrender. Using available parts and German technicians, they completed 9 Panthers in early 1946 for evaluation purposes. Standard British tank trials were carried out on 2 Panthers and 2 Jagd Panthers, but the tests had to be abandoned when the final running tank destroyed its transmission during a hill climb. The others had already been cannibalized for spares or had broken down from mechanical issues. The February 1948 report concluded that very little of practical value was learned due to the general mechanical unreliability of the Panther and Jagd Panther. Like the French, the British deemed the Panther technically fascinating but operationally useless. American testing at Aberdeen Proving Ground in Maryland also examined captured Panthers, though detailed public reports equivalent to the French findings have not been widely released. Several Panthers were preserved and studied at the U.S. Army Ordnance Museum at Aberdeen, which specialized in analyzing captured enemy equipment. U.S. engineers acknowledged the Panther's advanced elements, but also noted its many mechanical flaws. Their takeaways shaped post-war U.S. tank development, not through imitation, but through avoidance. They learned what not to do. How over-engineering for specific performance metrics creates systems that fail under combat stress. How complexity without reliability results in unusable weapons. And how impressive paper. Specifications mean nothing if a vehicle cannot be maintained or sustained in the field. The Panthers. Technological dead-end contrasts sharply with the Sherman's continuing evolution. Many WWII weapon systems remained in service or influenced later designs, but the Panther did not. While the German Bf 109 fighter continued to be produced in Spain and Czechoslovakia into the early 1960s, and Mauser rifles served worldwide for decades, the Panther disappeared. No nation adopted it once spare parts ran out. The Soviets briefly operated captured Panthers before scrapping them. Czechoslovakia and other Eastern European users replaced them quickly with Soviet designs. France and Britain, after exhaustive testing, also abandoned them. The design influenced no future tank in any meaningful way. The Sherman, by contrast, kept evolving. Its basic M4 chassis was adapted for dozens of uses: recovery vehicles, armored personnel carriers, self-propelled guns, rocket launchers, bridge layers, mine-clearing tanks, and flamethrowers. Its versatility allowed it to remain relevant long after 1945. Israeli engineers rebuilt Shermans into the M50 and M51 models during the 1960s and 70s, retaining only the hull while upgrading everything else: guns, engines, armor, and fire control systems. These upgraded Shermans successfully fought Soviet-designed tanks, proving that the original design had been fundamentally sound and adaptable. The Panther, on the other hand, could not evolve. Its intricate, tightly integrated systems left no room for modernization. It was built to do one thing well, and when that purpose passed, the design became obsolete. The Sherman stands among the most successful armored vehicles in history, not because it was flawless, or best by any single measure, but because it was reliable, easy to maintain, mass-producible, and trusted by those who fought in it. That blend of good design and superior logistics created a weapon that won a global war. The Panther, for all its engineering brilliance, stands as a warning. Technical superiority means little if the machine cannot reach the battlefield, cannot be repaired, and cannot be built in numbers. Complexity without durability leads to failure. History has rendered its judgment. The Sherman prevailed, the Panther did not. Not in isolated duels, but in the campaign that truly mattered: the struggle for production, logistics, and sustainability. American tankers understood that truth. They lived it, fought it, and won because of it. Nearly 80 years later, the lesson still stands. Wars are won by systems, not by specifications. The side with the better system, even with good enough weapons, defeats the side with better weapons but a weaker foundation. The Sherman versus Panther argument ended in May 1945, when Shermans rolled through Berlin while Panthers lay abandoned along the roads. The answer was never in doubt. Effectiveness in war is measured not by design brilliance, but by results.